Hi guys, welcome to part 2 of the video, all you need to know about capacitor markings and codes to fix stuff. So in this video, we're mainly going to look at actual examples of markings on capacitors. Please watch the first video first, otherwise you will not understand all of this, you'll be missing some knowledge. But just before we do, we need to look at another type of marking. These are, again, letters and numbers that we find on surface mount capacitors, but also some through-hole capacitors as well, such as film capacitors. So we'll look at these markings and then we'll actually look at some real-life examples.
So we have these types of markings. These are EIA markings, as they're called. If you see these two character codes, one number and one letter, so this is actually a 0, 0G, 0J, 1A, 1C. This actually is a voltage rating. You probably won't remember them, but you'll know what it is, so you can look it up. Just look for EIA voltage codes and you'll find these. And on surface mount capacitors, particularly surface mount tantalum and electrolytic polymer capacitors, you'll find an abbreviated version of this. So these are also EIA voltage codes. We have a lowercase e, which is 2.5 volts, and then the letters G, J, A, C, D, and so on, which are these various voltages. This is, for the main part, an abbreviated version of this. So you'll see 1A was 10 volts, and this is just A, 10 volts. 1C was 16, this is just C, and so on. So it's roughly based on the values here, apart from we don't have the higher voltage codes generally because these sort of polymer and electrolytic capacitors don't actually operate at those voltages. And you will probably find capacitors with these types of markings. Again, that's a 0, C0G, S1G, U1G. These are temperature coefficient ratings for the type of capacitor. So if it's important to you, if you see these 3 letter, or rather 2 letters and 1 number codes, that's what they are.
Okay, so I think we have enough information now, just about, to start looking at some real life capacitors. Let's see if we can work out the meaning of the markings on them.
So these are ceramic disc capacitors. These are the lowest values you're ever likely to find. So we have 1 picofarad, 2 picofarad. So if there's no multiplier, or like for example it says 2N, which would be 2 nanofarads, or anything else, we can assume this is picofarads. The black band at the top, by the way, this is a temperature coefficient. You can have different coloured bands, which means different temperature coefficients. So the temperature coefficient is how much the capacitance changes plus or minus per degree centigrade. The dot dash underneath, by the way, I wondered if this was Morse code, but I don't think so. I've actually Googled this because it's never occurred to me particularly what that means. And I've seen different, like dash dot and so on. Must mean something, but doesn't seem to be any definitive answer out there. So guys, what's the dot and dash mean? And you may see similar on other disc capacitors, like a different Morse code. I'll just add to this video here, guys. After I recorded it and I published part 1, I became more interested in these underlines on these ceramic disc capacitors and what they actually meant. So I had another go at Googling it, and this time I actually found something useful, I think. So we know the black or the coloured tip is temperature coefficient, and there are colours other than black, although the ones I have all seem to be black. And I found out 2 interesting things, so I'll tell you these. One is this underline. So if the value has an underline, that capacitor is a 50 or 100 volt capacitor. How you determine which, I don't know. If the value doesn't have an underline, then that is a 500 volt capacitor. Okay, so that's what I found out about these underlines. If you know any more on whether my capacitors with a dot dash are the same as just a dash, or does the dot dash maybe specify the 50 and the just dash maybe 100, that I don't know. Do you know? In that case, let us all know, yeah? Down there. The other thing that I spotted, and I haven't got any capacitors like this to show you, is you may find small value ceramic capacitors marked like this, 4R7. If you see these, the R actually just specifies the decimal point, like you find in resistors, 2R2 and so on. But the value is still in picofarads, even though it's an R. So 4R7 would be 4.7 picofarads. And you may also find ceramic capacitors like this. I haven't got any again to show you. Something like 2N2. The N specifies the decimal point and specifies nanofarads. So this would be 2.2 nanofarads. Okay, let's continue. Here are some more slightly larger. So these are marked 2.2. This is 22 picofarads. 22 picofarads. J is a tolerance marking, that's 5%. This is exactly the same system we find on resistors. So if you know how to read the tolerance on resistors, you'll know how to read them on these capacitors. The PH dash, I don't know. That is not a minus. These are not polarized. It could be 22 picofarads, but what the H and the dash is. Comments. But that one I don't know. I said that I know a lot of this stuff, but who knows everything? But after this video, I probably will. And here are some 100 picofarads, these three, so marked 101. This is the shorthand where the third digit is the multiplier, so 10 and one more zero, so 100. Mark the same. Notice this one, 1 kV, that specifies the voltage. You'll often find this on high voltage capacitors in particular. Another one there, 101. This is a different value, so this one, well, we'll turn it the right way up again. Same sort of marking, 821J. So 82 is the value, 1 is 10, so 820, that's the value in picofarads. And this one, J, is the tolerance. And once again, J is 5%. And then you'll find when we get to 1000 picofarads, we'll have them marked 102. But don't be surprised on vintage capacitors to find them marked as 100 if it's 100 picofarads. So you find capacitors marked 100, the chances are that is not a 10 picofarad. It's not like 10 and 0 more zeros, in other words 10. It is 100. Yeah, and you'll find that on old capacitors. So if you see 820, it's almost certainly an 820 picofarad capacitor. If you know it's an old capacitor, I'd say that is what it is. A few more examples then. So again, 471, 470 picofarad, 5%. Same value, 470, 470. HR, this will refer to the type of capacitor. I'm sure if we Google that, we will find that this is maybe 1000 volts or whatever voltage the working value is. That should tell you that. Again, 470. Here's another good example actually of what I was saying. So GU470, this is a 470 picofarad capacitor. It's not 47 like 47 and no zeros. It is 470. You will find this on old capacitors, so now you've actually seen one. We can actually just prove that. We'll get the capacitance meter and actually measure this. Yeah, it reads 520 within its tolerance. That's a 470 picofarad. Here we have some 1000 picofarads or 1 nanofarad, same sort of markings, 102, 1000, same bit of Morse code. This is another one, 102. This has some other markings on it actually, and I can't quite determine what they were. We have this R1C and this KRR 214. You'll often find these sort of additional markings on capacitors. I did think that R1C looks very much like one of these temperature coefficient codes. So I've looked up the remainder of them. I did say there were more, so these are the ones that I've actually found. This is the code, this is the temperature coefficient in parts per million per degree centigrade. You'll see that they're all negative, so as the capacitor warms up, the capacitance decreases. That makes sense because it's expanding. So as it expands, the distance between the plates increases. If the dielectric is expanding, so the capacitance would decrease. However, I've not been able to find R1C as one of those codes on the list, but I'm fairly confident that is probably what it is. Another example of the variations, all these say 104, so that these are 10 followed by 4 more zeros, or 100,000. So these are 100,000 picofarads, 100 nanofarads. But don't be surprised to find some capacitors that are marked 100N, which tells you it's in nanofarads. You can see these all use the same marking method. This one too, this one just has the tolerance 5%. This one different, so look, this has the mu sign 1, J. So this one, the mu sign represents the decimal point, so it's 0.1 microfarads, that's 100 nanofarads, the same thing. That's the J, I'm not sure about the other markings on it. This one again marked in a similar way, so 0.1 microfarad. This one has the voltage on. Now you'll see I mentioned this, so 275 AC, so that's actually telling you the AC voltage of that one. These sort of capacitors are generally used as filter capacitors. It also mentions 250 volts there, so I guess take your best guess on that one. Yeah. This marking X2, this is involved with this being a filter capacitor. While we're in this range, again 270 nanofarad, we've got a 220 nanofarad, so the same thing, 27 followed by 4 zeros, 270,000 tolerance. This has the voltage marked on this one, so you can see there are a number of variations. This one 0.22 microfarads, could be marked, to be quite honest, as 220 nanofarads. It's the same thing. Again, the X2 marking 250 volt AC. Another very similar, so this one just says 0.22. It doesn't mention whether it is picofarads, nanofarads, whatever, but by assumption we can work out this is a 0.22 microfarad capacitor, 250 volts. Again, the X2 capacitor, this is a filter capacitor. So these are the type of ones you normally find across the live and neutral connections on a switch mode power supply, for example. This one, so 270K. Now this is something I didn't mention earlier, but sometimes you will find this, like the K looks like a 1000. But to be quite honest, this is probably a tolerance of 10%. So 270 mentions the value, assumed nanofarads, or you could say 270,000, 400 volt. So you can see, I hope that working out the value of these is fairly intuitive, really. It's kind of like follow your nose to some extent. Okay. Another one. Again, this is the U rather than the Greek mu, 22. That's like the decimal point, 0.22 microfarads or 220 nanofarads. A couple of things I didn't just mention but was on that section of the video. One is these codes. So we see 2A473J, 2A823J. So the 823 value 82 and 3 zeros, 82 nanofarads, 47 nanofarads. The J is the tolerance. The 2A, this is a good example of something I did mention earlier because this is the voltage rating. So you'll see on the chart with the EIA voltage codes, 2A tells us this is a 100 volt capacitor. Another thing I want to just discuss a little bit at this point is these X2 or X and for that matter Y capacitors. X and Y capacitors. Let's just talk about those for a moment. X and Y capacitors. Actually, this is important. So X capacitors and Y capacitors are meant for filtering of noise on mains lines, live and neutral. The difference is that the X capacitor is designed to connect between live and neutral. Okay, and the Y capacitor connects from neutral to ground, earth. Okay, why is it important there's a difference? Well, if an X capacitor fails, it could set on fire. So because there's high voltages here, there's transients, there's spikes, these capacitors do get a fair bit of abuse in normal use, so they can fail. So to prevent them from setting on fire in the case of a failure, they are designed to go short circuit. So if these fail, they go short. Okay, and the idea of this is it blows the fuse. Of course, we did remember to put a fuse in here, didn't we? Okay, so it goes short and it blows the fuse. The Y capacitor is connected from one of the mains to ground. Now, I say neutral, but with, for example, an EU plug, the plug will go into the main socket either way, so it may be live. If this was to fail and go short circuit in the same way that does, it would actually cause a risk of electric shock because you're now shorting either live or neutral to ground. And you could end up with a piece of equipment that's actually working, it's just live, yeah, with the metal working live. So to prevent that happening with a Y capacitor, if these fail, they go open. They're designed to go open on failure. These are designed to go short. So that's what the X and Y capacitors are. This X2 we saw, well, we have X1, 2 and 3, and these are subclasses. And for that matter, we have Y1, Y2, Y3 and Y4. And these basically represent the peak pulse voltage, not the working voltage, but the peak pulse voltage if there's noise or spikes that the capacitor can handle. So an X1 will handle between 2.5 kV up to 4 kV. Yeah. X2, which are the common ones, the ones we saw, will handle up to 2.5 kV. So basically anything less or equal to 2.5 they will handle. And the X3, these are 1.2 kV. These are the common ones, certainly where we have 220 or 240 volt mains. The Y capacitors, well, Y1 has a voltage up to 500 volts. The Y2 is working between 150 to 300 volts. These are AC, by the way, AC voltages. Y3, 150 to 250 volts AC. And Y4 is less than 150 volts AC. So those are your X and Y capacitors. That's what they do. Do not mix them up. Yeah, when you're replacing these, do not mix these things up. Make sure you put the right type in. Otherwise, you could be electrocuting somebody somewhere down the line if you stick an X capacitor in there. Okay, carry on. A little larger again, 0.47 microfarads, so 470 nanofarads. Again, X1. This is a type of filter capacitor again, so these are the sort you find across the mains, and slightly larger again, so 105. So it's 10 with 5 more zeros. That's 1 and 6 zeros, or 1 million. So we have a 1 million picofarads, in other words 1 microfarad, tolerance J, 250 volts. So we see the same sort of patterns over and over again. This is around the sort of value of capacitor where we go more into the electrolytics. We can get them smaller than 1 microfarad. So let's have a look at a few electrolytics and how they are marked. There's a few different things to know with the electrolytic capacitors. I did mention polarity. You can see this is marked with the white stripe, the negative on. Normally these days capacitors are marked with a negative terminal, but on old ones they may be marked with a positive. value we can see 0.22 microfarads, 50 volts. This is quite a small value electrolytic, about the smallest you're likely to find. Another thing we'll see is the maximum temperature, 85C. So generally electrolytics come in 85C and 105C. This is important. So when you're replacing these, if you have a 105C capacitor, do not replace it with an 85C. You're okay going the other way, but not that way. Okay, so something else just to keep in mind. Here's a 2200 16 volts. Again, very typical capacitor. Minus sign with an arrow pointing to the negative lead. The manufacturer's name, low ESR 105C. Low ESR, this is a particular property of capacitors, ESR, equivalent serial resistance. This is basically the resistance of the capacitor to AC at high frequencies. This again is important. So if you see a faulty capacitor that says low ESR, be sure to replace it with another one which says low ESR. Almost always, in fact I would say always, the low ESR capacitors have 105 degrees C operating temperature. And a very, very large one, a really chunky one you can see. So again, clearly marked 10,000 microfarad, 100 volt. It's saying pins 1, 2, 3, 4. This actually shows you a layout of the pins. So pins 1 and 3, NC means no connection. Pin 2 is the 10,000 microfarad, 100 volts, and black says negative. So that's the negative end of the capacitor, which you can see here is that terminal. So that literally shows you which terminal is which on that one. And you'll find this on these very large capacitors, 85C. Okay, again, the white stripe with the negative signs on also shows you the negative. One thing I didn't mention earlier, I'll just mention it now because I forgot I meant to mention this. As we know, the value of the capacitor is generally stated in picofarads for small capacitors, nanofarads, sometimes we see microfarads, millifarads we don't really see written on capacitors, but you will see sometimes on vintage equipment capacitors marked something MF in capitals like this. So you might say you have something like 1800 MF, capital M. That is actually an antiquated way of stating microfarads. So this is microfarads, it's not millifarads, and it certainly ain't megafarads. Okay, so if you do come across that on vintage capacitors, the capital MF, it means this. So this one, this is the tantalum capacitor. There's a couple of things to notice with this. First one, the value 226. That's 22 followed by 6 zeros, or 22 million picofarads. This is 22 microfarads. With the tantalums, they are always, or as far as always as I would say, specified in picofarads. So you'll see things like 226. Also notice that the lead, which is marked as the positive lead, okay, with the plus sign. So that specifies the polarity, positive. A different type of electrolytic, this one, 150 microfarads, 100 volt. And if we look, this doesn't have any polarity marks on it. Okay, 85C, a manufacturer's name, and that's it. This is a non-polarized capacitor. That's what the NP stands for. So if you find an electrolytic that doesn't have any polarity marking on, it's almost certainly a non-polarized one. That means you can connect this either way in circuit. Also with capacitors like this, especially on vintage equipment, again in this like valve era, vacuum tube era, you'll find capacitors like this or similar to this that actually have more than one capacitor in parallel with them. So they'll have one common terminal and then 3 maybe other terminals. If you look on the side, it'll tell you it's 25 microfarads at 20 volts on one coloured dot, and another coloured dot is something like 5 microfarads, 400 volts or whatever. And these terminals actually have coloured markings on here. So you may find that if you're looking at vintage stuff, and you may also find capacitors like this with two terminals, no actual marking for the polarity on the printing, but one of the terminals is red and one is black on the little stud. So the red is the positive. So that's another thing you might come across if you're looking at vintage equipment. With these old capacitors I was just mentioning, they're not exactly connected in parallel, they just have a common terminal. So you have one common terminal, which is often the metal case, and also a pin underneath it. So you'd have something like 1, 2, 3, 4 pins, and they'd be coloured. So one might be black, one might be blue, one might be red, one might be yellow, this sort of thing. So coloured pins. And inside, as I say, effectively are maybe 3 capacitors. So the capacitors would be connected like this, effectively inside it. And this will go to this black terminal. And then these will be your various other colours, blue, red, yellow. And then printed on the side will be the values. So it'll say something like black common, and then it will say blue is, I don't know, I mean, it could be anything, 22 microfarads, 50 volts, and red might be 10 microfarads at 250 volts. The voltages on capacitors could be different, and so on. Now, these vintage capacitors are long since gone. If you're trying to repair this sort of equipment, just a hint actually, you could obviously replace this with 3 individual capacitors, but if you're trying to keep the kit looking as much as you can like it was originally, if you prise this top off the capacitor, the metal can, and you take all the crap, that's the faulty capacitors, out, you'll end up with a hollow can in the top. And then inside you can actually solder your 3 modern capacitors across these pins, put it all back together, bit of resin glue, stick the top back in again, and it'll look like the original. It'll still be the original case with the values on, but inside will be new capacitors. So just a little hint if you're working on that sort of stuff. Another type of through-hole capacitor that we haven't looked at, and this will be the last one for this part of the video, is going to be these things. So this is a leaded capacitor, HS47010V. 470 is the value, 470 microfarads, 10 volts. Okay, and while I was just looking at this, I realised there was a bit of a gap in my knowledge here, guys. How about that? Richard found a gap. So normally, if I'm using these capacitors, it's just to replace faulty ones, and I just stick them in the same way that the faulty ones were. And we also have some surface mount ones, the same sort of capacitors. And you'll see we have red ones, and we have pink ones, and we have blue ones, and I've seen green ones as well, and I've seen black. So this stripe on the end could be a variety of colours. Is it always a negative end? I was of the opinion that it's the negative end. Okay, and that's also because if you look at the leads, one lead is longer than the other. And just the same as with LEDs, the longer lead is the positive end. And we find the shorter lead there on with a blue one, and we find a one again here with a shorter lead where the red marking is. So that would suggest that that marking, regardless of colour, is negative. So that's what I'm going to say it is. What do you guys think? And is there any significance to the colour of the markings, or is it just whatever ink they put in the printer on that day? These are high voltage capacitors. Now, you need to be careful when replacing these. You see this one here, 103, 1 kV, so 1000 volts, 10 nanofarads or 10,000 picofarads. And then we see some capacitors that may look very similar. That one there, 102, so that's 1000 picofarads or 1 nanofarads. And they have different markings. This is SWCX. This X capacitor is another filter capacitor, whereas that is a high voltage capacitor, high voltage DC. These are not the same things, and they have some rather unusual markings on them. I would suggest, again, this is, you see, X1Y2 filter capacitor, 250 volts. You need to be sure when you're replacing these types of capacitors if they're faulty. I would honestly suggest, if you're not sure, to ask for some advice, because you could easily create a dangerous situation. The place I would ask for this information is badcaps.net, which is a forum. Yeah, I'll link it in the description here. So when it comes to high voltage capacitors like this, just take care a little bit on what you're doing. These capacitors, which look just like those other capacitors but with strange markings like SVC271-10, this one here, 14D431K, rather odd markings, ZOV, another one. Okay, you see it there. K300, S14. These capacitors are not capacitors. Okay, they look just like those blue things we were looking at, those high voltage capacitors, but they're not. These are voltage dependent resistors, or MOVs. They're normally connected on the input to mains equipment and elsewhere, effectively to prevent voltage surges. So those are not capacitors, okay? Don't let that confuse you when you see them. Likewise, these black disc capacitors are also not capacitors. These are NTC, negative temperature coefficient thermistors. This is a resistor that changes its value with temperature, often used to limit in-rush current on power supplies, so that when you first switch on, you don't get a massive current to charge the capacitors. So it starts at a high resistance, and as current flows through it, the resistance decreases practically to zero. So those capacitors are also not capacitors. Don't let that one confuse you either. And lastly, we have this thing. So this one, I don't actually know what it is. It kind of looks like a capacitor, but maybe it won't be a capacitor. If you're faced with something like this, I suggest you measure it with a capacitance meter and see what it actually is. So what is our mystery component? Just choose a range at random. Let's have a look. Well, if it's a capacitor, it's a low value one. Well, it reads like a capacitor. It reads 639 picofarads. Okay, so it sort of reads like a capacitor. Take the multimeter. Reads open circuit. So yeah, that reads like a capacitor. So there's a mystery one for you guys then. What do the markings on that one mean? Told you this was more of a complex topic than you thought. Yeah. And so concludes part 2 of all you need to know about capacitors to fix stuff. But what haven't we talked about? Well, we haven't talked about surface mount SMD capacitors. So you know what's coming, guys. Part 3. In part 3, I'm going to take another similar in-depth look at SMD capacitor markings. And we're going to talk about another major problem we find with SMD when we're trying to repair stuff, and that's a lot of MLCC, multi-layer ceramic capacitors, those brown things you find on PCBs with no markings at all. What can we do about those? Well, you just have to wait till part 3 to find out, yeah? See you all soon, guys. Ciao for now.